The reason why I'm being purposefully vague is because I want you to go through your work and to figure out what you missed. And that is part of science, is to sometimes struggle through a bit to figure out whether you have the right answer or not. Sometimes you have the right answer and you have to learn to have confidence in your answer. Okay? Because in science, there's no key. When they do an experiment, the only way for them to know whether they get it right is to do it again, or to do it a different way and see if they get the same answer. Okay? Or to have someone else work it and check with them. So I'll tell you in here all the time, I'll say, okay, check your answer with your neighbor. Because that's a common thing you have to do in science. It's because, like, I have the key, right? I make the key, but I make mistakes too. And in the real world, there's no such thing as a key, right? So the way you check yourself is you check with somebody else. All right?
Hey guys, I'll be checking with y'all.
And that is fine, because in the real world, that's called collaboration. Now, on a test, that's called cheating, right? But in this classroom, when you're doing homework, when you're doing labs, when you're doing things that we're working on in class, you need to collaborate with the people around you. If the people around you aren't helping you, then you need to get up and move somewhere else. Okay? So that they can help, somebody can actually help you. All right? Sometimes that's a challenging thing to learn because you have a lot of friends that are great friends, but and they're a lot of fun, but they don't help you accomplish your goal. All right? Now, I'm not saying don't be friends with them. You just might need to study with somebody else. All right? So you want to make sure that the person that you're working with is helping. You help them and they help you, right? Because then you both advance farther than you would have advanced by yourself. All right? Okay. So, yes, I'm being purposefully vague. I'm not telling you what the points are because I want you to go through and check, because that's the way that you'll actually really learn it. You want to work together? I dare. Actually, go ahead.
Now?
Not now. But what I want you to do is on Thursday turn in, and so that we have an easier thing for me to look at, will you please, you don't have to rewrite the problem, but will you please put it on a separate sheet of paper, just number it like part A, I, or whatever it is, and just and show me all your work, okay? Please show me your work, because I'm going to grade it like I would have normally graded the test.
Mr. Brown, just tell us the answer so when I finally get to something, I know if I'm in ballpark or anything.
The answer contains numbers and letters.
So I'm in ballpark.
Maybe a symbol.
You see, it's so country.
All right, we're starting something new. Actually, not really new. We're just migrating to something a little different. We're going to take a little segue today. Segue. All right. Hopefully, I have enough of these. We're beginning a chapter called, or a study called thermodynamics. All right, thermodynamics is an extension of what we just learned, which is energy and work.
And these ours?
Yes, these are yours. All right, can you fight over the orange ones? Okay, take this thermo packet. Take this thermo packet, set it aside. You won't need it for today. All right? We're starting a new unit. Our test for this unit will be on the 23rd. Okay? So we've got it'll be 3 weeks in this unit. All right, we have 4 e-homework assignments, number 4 through number 7. They should be open and available for you to see on e-homework, on the e-Quest system right now. And our first one is due on the 9th, which is Thursday. I truly encourage you to download number 4, the one that's due on the 9th, on Thursday, and start it early. Okay? Because this is the one that covers gas laws. Oh, you know what? That's not the really hard one. The harder one is the one on the 5th. Sorry, the one on the 13th. It's number 5. Make sure you start number 5 early. It's our second one that's due in this unit because it's the hardest one. Probably it has crazy unit issues. It's a little more challenging. Okay? So make sure you start that one early. All right. Okay, so let's see if we can get you everything you need to know for e-homework number 4 and just the beginning of thermo. All right. Okay, now we took a lot of time to go over the test, but it's important to do that for our first test so you have an idea of what they're going to be like.
Yes, it is.
Thank you for that vote of confidence. I appreciate that. My life is complete. Thank you.
Oh, I said something.
All right. Thermodynamics. Thermodynamics is the study of, it's the extension of the study of energy, conservation of energy, and work. Okay? It adds new stuff onto what we've already studied. It adds the idea that there is a new way to directly transfer energy from one place to another. The only way that we've talked about so far is work. Work transfers energy from one place to another. But heat also is a direct way to move thermal energy from one place to another. And then we're going to talk about thermal energy in more detail. Okay? And why it's unique amongst all the different types of energy. But before we do that, we have a couple of odd topics to kind of go over, make sure we understand them. And then we also need to talk about gas laws before we talk about thermodynamics, because gases are really important in thermodynamics, because gases are unique amongst all the different substances, which allow us to do things in thermodynamics. All right? So here we go. First off, let's talk about thermal expansion. And it's going to be one of the little topics that gets thrown in here real quickly. Okay, thermal expansion. Let's think of solids first. The solid is easiest. Okay, in a solid, you have atoms which are connected to each other by bonds. All right, so like for instance, if we had a cubic structure of atoms, okay, and the atoms are connected by bonds, then when we have thermal energy, remember, we talked about thermal energy, right? What is thermal energy?
Kinetic energy of the particles.
Not just kinetic energy, but kinetic energy is part of it. So this molecule can move. And if it moves, it has kinetic energy. But when it moves, it's attached to the other ones around it, right? So if it moves from here to here, then the bonds that connect it will be stretched. Okay? And when the bonds are stretched that connect the atom to the overall structure, that is a type of potential energy. It's like elastic potential energy. Not the same as, but it's like that. So you would stretch it or compress it If you compress them too close, they'll repel. If you stretch them too far out without breaking them, it will pull back in. And so what happens is that inside of an object, the atoms, the molecules, they're all moving all the time. The only time they stop is if they're at absolute zero, which literally means no more motion. Okay? No, well, you'd be dead long before that because you're a warm-blooded creature. Okay? But as the temperature gets lower, the kinetic energy gets less, and the bonds get stretched less until you get down to, excuse me, zero kinetic energy. Now, we can't really get to zero. So what we end up with is all objects that have any temperature at all will have a kinetic and potential energy, each one of its atoms. But the thing is that this is random motion, all right? They're all moving around, all random. This one's sitting still, then all of a sudden it's moving, and then it's sitting still again, then it's moving this direction, then it's moving that direction, and it's all random. We know it's random because, like, for instance, this marker, or this eraser right here, okay? The molecules are moving around. How can you logically prove that the molecules in here have random motion? Yeah, who said it? It's not moving, right? If it wasn't random and there was some organization to it, like they all moved that way at the same time, then it would move, right? Does that make sense? So, in theory, statistically, maybe all the molecules could all of a sudden just decide to move in this direction at the same time. But because there's so many molecules and it's random, they don't ever line up like that. So the object as a whole sits still. But what does happen is when the object gets warmer, they move faster. And when they move faster, they stretch the bonds a little bit more. Okay? And when they stretch the bonds a little bit more, the object expands. Okay? Some of you have noticed that. Like if you wear a ring or sometimes clothes in the summertime fit tighter. Rings are tighter on your finger in the summertime than in the wintertime because your body has expanded in the summertime because it's warmer.
You get fat in the summer.
That's right. You get
That sucks.
you get thermal fat in the summertime just for swimsuit season, right? Now, how much is this expansion? Well, it's quite small in most cases. All right? All right, here's our equation for thermal expansion. It goes like this. Delta L equals alpha L naught delta T. I want to find that on your equation sheet. Make sure I've written it exactly the same. Sometimes I write it with small l. Sometimes I write it with big L. But it's a D? That's a delta. Is it on there in thermal physics?
Yeah, that's right. That's how, yeah, but it says
They use little l? Okay, let me write it the way it's on the equation sheet. Okay, they use little l. Okay? Alright, this is the change in length of the object is equal to alpha, the original length, and the change in temperature. So L equals length. Delta means change in length. The 0 means the original length, or the length at time equals 0 sometimes. Okay, delta T equals the change in temperature. Okay, that's in degrees, that's in Kelvin, but it could be also in degrees Celsius because Kelvin and Celsius, the change is the same, right? The change between, what, 273 and 373, freezing and boiling in Kelvin, is the same as between 0 and 100 in Celsius, right? So, this could be this or degrees Celsius, because it's delta. The length is in meters. Alpha is a coefficient. Coefficient of thermal expansion. Now this is a tiny number. So like for instance, Coefficient of linear expansion or thermal expansion. It might be called thermal expansion or linear expansion. It's the same thing. For gold, alpha for gold equals 1.42 e to the negative fifth degrees Celsius to the negative 1 power. So it's got a unit of 1 over degree Celsius. Okay? That means for every degree Celsius, you rise the temperature of the gold. It will expand that much. Well, what is that? That's 1, 2, 3, 4, 1, 4, 2. For every degree Celsius, it'll expand that much.
4, 5. I think it's 1 less 0.
1, 2, 3, 4, 5. Right there? 0.0?
Yeah.
Yeah, there we go. I forgot my decimal point. Okay, it's not very much. So you have to have a very large increase in temperature for you to notice most of these things.
And that's in meters, right? How far it goes?
Well, what ends up happening is this is in 1 over degrees Celsius, this is in meters, and this is in degrees Celsius. So those will cancel. So it's like meter per degree Celsius. So it's a tiny amount. So decimeter, centimeter, millimeter, it's like 1/100th of a millimeter per degree Celsius. It's very tiny. Okay? So you don't see much of a change unless the object is really big. Unless it's really big. All right? But this does occur, and it's very important that we take care of it. Okay? Everybody get up. We're going on a field trip.
Extra bread.
Column in the corner back there. You see that spongy stuff? Okay, that's an expansion joint. When this building gets warmer or colder, the different parts of this building expand and contract. When it expands and contracts, the building can crack. And these things are made so that when the building gets larger and smaller, those flexible joints will hold it together. Okay? There's a big one out here in the hallway, too. Okay.
That is juice.
That's a tooth.
Oh.
All right. Your tooth. You get a cavity. They drill out your tooth and they put a filling in.
It's 5 centimeters.
5 centimeters.
That's how precise it is.
You need to measure a little closer than that.
That's what we have. That is precise. Mr. Grill, we didn't round or anything.
I was wondering how. I was like, what is this trick to me?
Please. All right. You have a filling. You eat something really hot. When you eat something hot, the temperature goes up. What happens to the size of your tooth? It gets bigger. Wait a minute. What if the thermal expansion of your filling is different than the thermal expansion of your tooth? It could do one of two things. What if the thermal expansion of your filling is smaller than your tooth?
Well, then it's going to separate from the tooth.
Yeah, when your tooth gets bigger, the filling doesn't get bigger fast enough and could fall out. Which is better than the alternative, which is what if the thermal expansion is bigger for the filling? Then when you eat something hot, then it could expand faster than your tooth and crack your tooth, right? So they make this material so that it has the properties similar to your tooth, or at least is soft enough that it will stretch and compress, right? Okay, when you go home tonight, I want you to get a pot. A pot.
Oh.
Put it on the range.
What's a range?
It's a stove.
Okay.
So what's a range?
Home on the range. Put it in a field.
I thought it was, yeah.
Put it on the stove, not in the oven. Okay, get a glass of water and fill the thing up, and then slowly fill it up so that the pot
You drew it wrong. You had like.
That you filled it up so it's slightly bubbled above. So that you filled it up to the very top, okay? Now, you can keep adding water, and because of surface tension, it will actually bubble up above. But then turn your oven on. Sorry, your stove on. That range thing. Turn it on, and then watch it and see which one has a bigger thermal expansion coefficient, water or the pot. If the water has a bigger thermal expansion coefficient, what will happen?
It's an expansion.
It'll expand faster and it will bubble out.
That's what happens when you make something, make something and it goes whoosh.
That happens when you make something and it goes whoosh. Okay, now during the explain part of problems,
It's like,
to justify your answer, you need to be a little bit more specific than you put the stuff in and it goes whoosh.
no white foam comes over it. Yeah?
All right, if the metal has a larger thermal expansion, then the water will go into the pot, right? So I want you to go home and do that tonight. Put it on the stove, pour water in, and heat it up. But don't make it boil. Just get it warm.
I was going to say, what about when the pot expands? It would also go in, which would make it so it actually has.
Now that is a common misconception. If I have an object like this, like a sheet of metal, and I cut a hole in the metal, okay, and I heat the whole thing up, does the hole get bigger or smaller? Okay, it's the same thing like a ring. If I take my ring and I heat it up, will the hole on the inside get bigger or smaller? Here's what happens. If you take a ring, and if you were to cut it and lay it out flat, it will look like this.
It would stretch both.
Now, why is this side a little bit bigger than that side? Because its circumference is slightly bigger than this circumference, right? Now, if I was to heat this up, what happens is the whole thing gets bigger.
Stretches both.
But what happens is that means that the circumference here gets bigger when you roll it back up. So what happens is the ring gets bigger, the hole gets bigger, the outside gets bigger. It's like you put it on a copy machine and just hit 105% and expanded 5%. Everything gets bigger.
Right, and I guess so it does expand inward, but it expands enough outward that makes up for it.
That's
I guess
correct.
Just because it's squared for.
That's correct. So
area.
some of you have done this before. You have a jar at home that you can't get the lid off of. What do? You stick it under the hot water and you get it hot, and it expands and it loosens the lid up. You crack the glass and pour it out.
I've never had that problem because I was told.
So brawny. You got Popeye forearms.
I thought when the can was good before.
All right. So everybody, you'll see this in concrete sidewalks as well. You'll see the gaps. There'll be a section of sidewalk and a gap, and another section of sidewalk and a gap. That gap is for the expansion, so that the sidewalk won't crack. Okay? All right.
The sidewalks do crack. Just a manger.
They do crack anyway, but they would crack more. Okay, there is an equivalent one. It looks like this. Delta V equals beta V naught delta T. Okay, if this is linear expansion, this would be
Vertical.
Parabolic.
it would be volume expansion. So this is the volume. This is the coefficient of volume expansion.
What is that symbol in front of
Oh,
V?
and
Beta.
That's a beta.
Beta.
And that's delta T again. Okay? So that's if the volume is changing. All right? So there you go. Linear expansion, volume expansion. There's a couple of questions about this.
Wait, can we redo that?
Okay, because I'm looking here at the first one in number 4, and you know, I understand how to use the equation, but for the first one, it doesn't give us any coefficients. What would
It doesn't?
Not the first one.
Yeah.
Okay, hang on.
That's what I was wondering.
Is that one of the ones you have to look up? Hang on, let's see, what is it for?
Gasoline.
Yeah, gasoline.
All right, good question.
What question are we?
Excellent question. Okay, e-homework, number 4, problem number 1. Thank you for pointing that out. Beta for gasoline is 0.00096. 1 over degrees Celsius.
After the decimal.
Yeah. I write it the engineering way, which is 0.3096. You will need that. Thank you for bringing that up.
And then what about steel for number 2?
Number 2, is steel not given?
Nope.
Ooh, you know, because these are all things that you look up in your textbook, but I'll give them to you.
Yeah, I was going to say gold is given on 3.
Yeah, gold is given on number 3, but steel is not given. So here's steel. Alpha for steel. Oops, steel. Steel. I wrote steel the wrong way. Steel. Equals, where is it? 1.1 times 10 to the negative 5th, 1 over degrees Celsius. Okay? So those are your coefficients that you will need for number 1 and number 2. All right? Write those down for your e-homework. Number 3 is given.
How many questions are there?
7.
Yeah, this is a short one. There's only 7.
Good.
All right, now,
Who's singing? You have the voice of an angel, Mr.
a short-hauled angel, but an angel nonetheless. Thank you. All right. Now, let's talk about, that's thermal expansion. That's one of those little side things you need to know. The next thing you need to know is, you need to know about heat transfer. Let's talk heat transfer for a minute. Or 2. All right, there are 3 ways to transfer heat. Number 1, conduction. Number 2, convection. And number 3, radiation. All right, conduction, convection, and radiation. All right, help me out here. What's conduction? Yeah, physically touching. Now remember, we talked about the atoms moving around and bouncing around real fast, right? So if you turn on your stove, you turn on your stove, wait for those coils or whatever kind you have to get nice and red hot, and then you touch them.
Oh,
Yeah.
You're incredibly intelligent.
Don't try this at home.
Or anywhere else.
Try it in Dr. Tuttle's. All right. Let's find out. No. All right. The deal is, everybody, when you turn on your stove, if you touch it, the reason why it burns you is because the molecules are moving so fast that when you touch them, they collide with your molecules, transferring that energy from them to you by collision. It's like if the hallway's crowded at passing period, and you go out there and run down the hallway.
You're going to hit somebody.
You're going to hit somebody, and you are a fast-moving molecule colliding with a slow-moving molecule, and energy transfers from the fast to the slow, right?
Oh, with this ruin. On Sunday, I went into a tree at full speed, and then I got hit. Yeah.
Yeah, just like that.
Yeah. It happened just in time for the sun.
Okay, now there's an equation for how quickly this heat transfers by conduction. And here you go. It looks like this. H equals Ka delta T over L. Now look up in your equation sheet. Is that the way it's written on your equation sheet?
Yeah.
Is it written just like that?
Yeah.
All right, so what are all these things? Okay, H equals rate of heat transfer. So rate of heat transfer.
The unit would be in.
Yeah, what would the joule? What would the joules? What would the unit be for that? It's not joules.
It's rate.
It's rate of heat transfer. So it's the rate of joules, which would be watts, right?
You gotta get more centralized.
Centralized?
Why?
That is not an answer. Think about how I write this on my paper, and you're writing all this, and you're going,
All right.
yeah, or
What's K?
That gives thermal conductivity.
Thermal conductivity. Okay, now wait a minute. Thermal conductivity is a constant.
Happens to be.
Now that constant needs to be given to you, or you'd have to look it up, or you'd have to be given all the other things and solve for it, right? Now thermal conductivity, think about that for a second. What kinds of materials will have a low thermal conductivity? Styrofoam, rubber, paper, cotton, things you make to insulate, right? Like you want your winter coat. You want your winter coat to be made of things with low thermal conductivity. Bubble wrap. So you could make your winter coat out of newspaper and bubble wrap, and you would be nice and toasty. Hey, think about it for a second. Shh, think about it for a second. Like down feathers, like a down blanket. What's significant about a down blanket is that the little downy feathers take up a lot of space and trap air pockets, right? Just like bubble wrap does, right? Air is a poor conductor of heat, okay? It's a poor conductor of heat. So you want something that's airy. Actually, a vacuum is a great, well, has a very low thermal conductivity, right? Yeah. All right, so in fact it would have a zero thermal conductivity, right? There's no molecules. All right, so double pane windows. A double pane window has a window here and a window here, and has an air pocket or a vacuum pocket in the middle because it has a very low thermal conductivity. And so your window, you can still see through it, but it insulates better. Okay? All right, A is the area of contact. Delta T, of course, is the difference in temperature. And L is the it's the thermal conductivity path length.
Oh, okay.
All right, now let's.
Think it is.
Yeah. So think about this. This is the way this works. Is if I've got a hot area over here and a cold area over here, temperature hot, temperature cold, delta T is the difference between these two. Okay? And then what they're talking about is the material in between these two. This is the area of contact, okay, between the two. And this is the length of the path for the heat to flow from one to the other. Does that make sense? So if you think in terms of like insulation, Okay? You have a thermal conductivity of your insulation. You have an area of contact. Like for instance, if you want to insulate the ceiling, then like these ceiling tiles insulate. They have a certain surface area, and they have a certain thickness. That make sense?
So then, would the area of contact by the conductivity pattern be equivalent to like a volume of conductivity?
Yes. Well, this is in the numerator, that's in the denominator.
Yeah, but I'm just saying, if you were to multiply, would it be like some sort of
Yes.
volume?
Yes. All right, so think about it for a second. If you want to have a good insulating material, then what's it like? Well, if you don't want this heat transfer to be very great, then you want to have a material that's, well, tell me what it wouldn't be like. What kind of materials have a high thermal conductivity? Metals. You know why metals have a high thermal conductivity?
They're dense.
Not necessarily. But density does help because the closer the materials are packed together, the atoms are packed together, the quicker, easier it is to transfer that energy from atom to atom. That is correct. The more dense the material in general, the faster it'll conduct heat. Also, the big thing though for metals though is what's different about a metal than a non-metal? Yeah, it has those free electrons that float around the surface. Those electrons can transfer the heat really quickly as they float through the material. All right, so you want something that's a non-conductor or a low thermal conductivity.
Minimum area.
You want minimum area of contact. You want
temperature,
less temperature difference
but a greater thickness.
and a greater thickness. So most of the time when you build a house, you don't have control over where it's built and what the temperature difference will be, although you can change your thermostat in your house. This is why they say in your house or apartment that in the summertime you should have the temperature inside your house warmer because you decrease this so you waste less energy. And in the wintertime you should have your thermostat lower so it's closer to outside temperature. So again, this is smaller. So you can make your insulation thicker. But you can't usually change the surface area of your house unless you build your house different from the beginning.
Make a box house instead of a rectangle house.
Actually, if you build a circular dome house.
Maximization calculus.
Yeah.
Yeah, that's
All right. We're going to quit there. We'll start up with radiation next time.